In this video, we'll learn how to collapse sines and cosines into a single periodic function. Now, what cases am I talking about? Well, when you encounter a situation adding cosines and sines with the same argument, for example, y equals a cosine of omega t plus b sine of omega t, with arbitrary scalar constants in front, which in this case are this a and b, you can actually write it in the form of one periodic function. This should make some intuitive sense, since if two functions have the same frequency and period, adding or subtracting them should result in a periodic function with the same frequency and period. In most cases, it's convention to combine the two into a single cosine function, so we'll stick to this as well. So how would we do this? Well, first we recognize that the frequency of the new cosine function should be identical to the original sine and cosine frequencies that you're adding. So this would be this omega and this omega. Again, note that the frequencies, the coefficient of the time variable of the two original functions, must be the same. So if we labeled these omega 1 and omega 2, we can just say that omega 1 must equal omega 2. So taking advantage of the constant nature of the frequency, we can focus on the magnitude and phase change of the final cosine function. To do this, we will create a right triangle. So we can make a right triangle like this. We'll call this side A for the cosine coefficient and this side B, and then there will be a phase change of alpha. If you've taken physics classes before, this technique should look pretty familiar to you. Making the two into a triangle allows us to evaluate the individual contributions of the sines and cosines. From a geometric sense, the hypotenuse that we label C will be our final cosine function. Our final function will be in the form C cosine of omega t minus alpha. Say that y equals C cosine omega t minus, and alpha is the angle here. Now we can just use basic geometry from here to find C and alpha. So C, of course, is the square root of a squared plus b squared, in case you didn't know. And alpha equals the inverse tangent. I'll move this over here. So alpha equals the inverse tangent of b over a. Tangent is opposite over adjacent. Be sure to note, though, that alpha is in radians, since omega t is a dimensionless quantity. So you have frequency, which is radians per second, and time, which is in seconds, or it doesn't have to be seconds, it can be in minutes, hours, whatever. So you end up with radians regardless. So you can see that this is a pretty simple process. One thing to be careful of, though, is when a or b is negative. In that case, you'll have to consider the different quadrants of the coordinate plane, and this will make more sense in the next example. So let's try one. Let me clear this off. So let's say we have the function y equals 3 cosine of 4t plus 4 sine of 4t. Pick these numbers so that the final numbers would be nice. So from here we can draw our triangle. So we can say that triangle. Try that again. So we call this angle alpha, and we call this side 3 and this side 4. Note that if I move these sines and cosines around, switch them, these would still be 3 and 4. This would still be 3, this would still be 4, because this cosine, the coefficient of the cosine will always be the bottom angle, because cosine is adjacent, right? And same goes with sine. So now we can calculate the actual numbers. So c equals square root of 4 squared plus 3 squared, which equals 5. So that will be our final cosine coefficient. Our angle, however, won't be as nice of a number, but we'll calculate it anyways. So our angle will be alpha equals inverse tangent of 4 over 3, opposite over adjacent. And this final number will be about 0.9273. So now we can write out our final function. So our final function would be y equals 5 cosine. We would take our original frequency, which is this 4 right here. So we get 5 cosine of 4t minus 0.9273. Pretty simple. So let me demonstrate now what happens when we change one of the coefficients to a negative. So let me clear this off. Now we can use the same example as before, except instead of 3 for the cosine coefficient, we can say it's negative 3 this time. So negative 3 cosine of 4t plus 4 sine of 4t. So now we can draw our triangle. However, it will look different this time. So notice that the coefficient of the cosine is now negative. So that means we will be in the second quadrant. So let's draw our axes. Now our triangle will be over here. So if we label the sides, this will be 3 and this will be 4. And however, in this case, our alpha will now be this quantity. Now we could do negative angles and all that jazz, but I just like to keep it in terms of the form c equals, or not c, sorry, y equals c cosine of, try this again, give me more room, y equals c cosine of omega t minus alpha. So this alpha will always be the angle as referenced from the positive x-axis. So to make things more simple, we can define this angle of the triangle as, say, phi. So phi is, of course, inverse tangent of 4 over 3, which we calculated in the last example, which equals 0.9273. So alpha will then in turn be equal to pi, remember we're in radians, minus 0.9273, which will equal 2.2143, approximately. I rounded. So now we have our alpha and our coefficient as well. Well, actually we didn't calculate our coefficient. Our coefficient will simply be c equals negative 3 squared plus 4 squared. This is a 3, which of course will just equal 5, since the squared takes care of our negative. So now we get our final function, which is y equals 5 cosine of 4t minus 2.2143. So now that you have a pretty good idea of how to sum sines and cosines, you can just stop watching if you just wanted a refresher on how to do it. Or keep watching to see the proof of this method, which I highly recommend. So going back to the general case, let me erase all this. Going back to the general case of y equals a cosine of omega t plus b sine of omega t, we will again draw the triangle that these components create. So this is alpha A and B. Now we will use the cosine addition formula for this proof. This is a trig identity. You probably don't know this off the top of your head, so I'll write it out. It is cosine of alpha minus beta is equal to cosine of alpha times cosine of beta plus sine of alpha times sine of beta. Now, it may not be immediately obvious how to get the general case, this general case, into a form like this. So to do so, we will pull out a factor of c, which is the magnitude of the hypotenuse, to get y equals c, we pull that out, times a over c cosine of omega t plus b over c sine of omega t. So notice that this c right here multiplies everything. So at this point, if you're paying close attention, you may notice that the a over c and b over c terms look quite familiar. In fact, we can rewrite them as cosine of alpha and sine of alpha, respectively, to get y equals c times the quantity cosine of alpha times cosine of omega t plus sine of alpha times the sine of omega t. Close parentheses. So now it's pretty obvious how to get to the form cosine of alpha minus beta. Let me just rewrite. I assume that you wrote down the cosine addition formula from before, so I guess I won't rewrite it. So notice now that since cosine is an even function, which means that cosine of alpha is also equal to cosine of negative alpha. So it doesn't matter which we pick as our alpha and beta in our original equation. I guess better variables could have been picked since we have an alpha in the original, but what I'm talking about is this alpha and omega t term. We can call either of those alpha or beta. However, we usually call omega t alpha just by convention, I guess. So after using the cosine addition formula, we finally end up with the desired form, y equals c cosine of omega t minus alpha. So that's it for adding sines and cosines. Hopefully this was helpful and maybe even enlightening in some way. So thanks for watching.